So in this lecture we are going to talk about the access and modulation, which is the third part of block 3. We will start talking about the time division multiple access used in GSM networks. Then we are going to talk about the code division multiple access, the CDMA, which is used in the UMTS and third generation networks. In particular, we are going to talk about the channelization codes and scrambling codes. Then we will talk about the orthogonal frequency division multiple access, the OFDMA, and some brief talk about modulation and symbols and the quadrature methods or quadrature amplitude modulation CAM. Time division multiple access is one of the key access technologies used in GSM systems. How it works, the band of frequency, whether in the uplink or downlink, is divided into a set of channels, and each channel will be used by different users through the division of the channel into a time slot. If I'm looking at the GSM, I will see that I'm mixing two types of multiple access technologies, in fact. So I'm using first the frequency division multiple access in order to divide the bandwidth into a set of channels. Then I will be using the time division multiple access in order to divide or to allow the access for different users to each of these channels. This is why we can say that GSM is mixture of time division multiple access and frequency division multiple access. So let's have a close look on the time division multiple access. As I said before, this is applied in each of the uplink and downlink and each channel of the uplink and downlink bandwidth, frequency bandwidth. So how do we do the time division multiple access? So packet information bits are transferred or transmitted in frames. Each frame is, the duration of each frame is 4.615 milliseconds. So how I will allow a certain number of users to use the channel. So each frame is divided into a number of time slots, which is 8. So I will have 8 time slots for each frame. A simple calculation will lead to find that the duration of each time slot is 546.5 microsecond. Within these 546.5 microsecond, I will be transmitting 114 bit, and we will use these numbers to calculate the bit rate later on. So each time slot will be allocated to one user. So we can see the different frequency channels and the 8 time slot for each frequency and for each channel, and then I will allocate a certain time slot on a certain frequency channel to a given user. Note that the frequency channel is of 200 kilohertz. So if I want to be accurate, I cannot say that users have simultaneous access as we said before, given that the user is accessing the channel in a certain time slot and then it will wait to the next time slot to use the channel again. So at a certain time t on a given channel, I have only one user. So the turn will come every frame duration, which is 4.615 milliseconds. And then the user will have the time to send the data again and again. So every 4.615 milliseconds, the user will access the channel and then he will send the data. And during this 546.5 microsecond, which is the time slot duration, the user will send 114 bit. So if I want to look in virtually, the frequency channel consists of the time slot allocated to a certain user over the different frames. So I can call this the user's communication channel. And note that the user cannot change this time slot between the different, within the same communication. The user is allocated a given time slot, so he cannot change it in every frame. Example, if I allocate the time slot number 1, so the user will send in the first time slot of the first frame, and then the first time slot in the second frame, first time slot in the third frame, etc. In fact, not all frames are dedicated for user channel. 1/13 of the frames are reserved entirely for control data. So let's use these numbers to calculate the bitrate, user data bitrate in GSM. So as we said before, so every frequency channel contains 8 time slot. We will call each of them a GSM channel. So if a frame lasts for 4.615 millisecond, a simple calculation, I can find that the frequency equal 1 over the time period, and then we can say that the frequency of frames per second is 1 over 4.615 milliseconds. So I'm converting to second, and then I will have 216.7 frames per second. So given that each slot in a frame contains 114 bits, what will be the data rate in bits per second for the GSM channel if I will forget for the time being the control data? So I will consider that all frames so far are used for data, for users' data. So I have 216.7 frames per second, and within each frame I'm transferring, so it's frame per second, and each frame I have 114 bits per frame. So I can calculate the bit rate for a given user. Again, this is for only one time slot. So the answer will be 24,700 bits per second in one direction again. So it is whether in upload or in download. So now if I will consider the fact that 1/13 of the frames are used for control data, so I will have only 12/13 frame. So the real bitrate will be the 24,700 bit per second, but times 12/13. Given that over 13 frames, I will have 12 for users data and 1 for control data. So the bitrate will be 22.8 kilobit per second by multiplying the 24,700 bits per second with the 12/13 factor. So the question is that we have increasing demand for data, and then we have a continuous need to increase the bitrate. So the first improvement was in the GPRS. So in GPRS, in order to allocate more bitrate, to have more bitrate per user, what we will do is to allocate more than one GSM channel. And in practice, there is a threshold. We cannot allocate all the 8 time slots, and usually we allocate up to 5, and this parameter is customizable. So this is in GPRS, which is the 2.5 generation. And in order to have more bitrate, and this is done in the 2.75 generation in Edge, we use what we call multi-level signaling, and I believe you are aware of the concept of multi-level, which we have seen before in the memory technology when we have multi-level flash memory. So this is the same concept. Instead of storing 1 bit, or of sending 1 bit of data during a certain time, we will be sending one symbol that consists in more than 1 bit. So this is the principle. Usually we send only 1 bit during this time. So what we will do, instead of having only a symbol of 2 states, we will have a symbol, for example, of 4 states. And by sending each symbol, we can accommodate to send 2 bits instead of 1 bit. And you know that the number of symbols equal 2 to the power number of bits per symbol. So if we apply this, if we have 4 symbol, we have 2 bits, which is given that 4 equal 2 times 2. If we have 8 symbol, we have 3 bits, 8 equal 2 to the power 3. So this is the number of bits. So the advantage is that we are increasing the bit rate, but the disadvantage is that we are more vulnerable to noise, given that when we have multiple symbol, the the voltage will be the voltage corresponding. If we have to have a clear idea, we can look at the symbols at a certain signal that are getting closer to each other. So if we have a smaller noise, we can move from one symbol to another symbol. So this is why if we increase the number of bits per symbol, we are more vulnerable to noise. And we should be familiar with certain concept we are using when we are using multiple level, which is, instead of saying bit rate, we say symbol rate, and the relation is that the bit rate equal the symbol rate times bits per symbol. So if I have 3 symbols per second, as a simple example, if I have 3 symbols per second and 2 bits per symbol, so I have 6 bits per second. An additional refinement of Edge is by providing more extra coding scheme. And we will see some aspects of how to choose the appropriate coding scheme or coding rate depending on the radio channel condition. So what we have to retain is that Edge provides a set of coding schemes, and we can select the most suitable coding scheme depending on the conditions of the channel. So in favorable circumstances, we can attain up to 300 kilobit per second, and based on the definition of mobile broadband, even though we said at the beginning of this block is that mobile broadband should have a bit rate above 300 kilobit per second, but based on these requirements, and as I said, even though we said that these numbers are now above this threshold, so Edge can be considered as a mobile broadband technology regarding the bit rate. So now let's consider one of the main limitation of the GSM or and its enhancement. So I'm talking about the second generation, 2.5 generation, and 2.75 generation. So the main limitation is that the resources are finite in these technologies. So if I have a fixed number of GSM channels, I cannot go above this number. So if I have an exceeding demand for a certain technology, the only solution available is to replace the large cell with smaller cells, such that we decrease the size of the cell in order to increase the number of users that can use the technology in a certain region. So the solution to this problem comes with the code division multiple access, which was an alternative to the time division multiple access in second generation, and you can refer to the figure that shows the evolution of mobile technologies, where you can clearly see that CDMA was a technology adopted in certain countries for the second generation. Now in third generation, the CDMA is used exclusively, and one of the most important aspects and advantages of CDMA is that it has less definite limit on capacity. So I can have an increasing number of users, but when I increase the number of users above a certain threshold, the quality will decrease, and thus the limit is not that strict, but we can increase it, but on depend of the quality of calls. So the advantage now is that we are providing the multiple access based on code, and this is why we use the term code division multiple access. So no need now to differentiate between the frequency used in adjacent cells, and now all the frequency band can be used in adjacent cells. And this is a big advantage compared to the TDMA and FDMA. used in GSM. Another advantage is what we call the soft handover. Given that in GSM adjacent cells use different frequency bands, and thus when the user is moving from one cell to another cell, he has to cut off the previous connection and open a new connection on a different frequency when he moves from one cell to another cell. And this is what we call, this is a hard handover. While in CDMA, the user can keep using the same frequency, but what he has to do is to change the code when moving from one cell to another cell. And this is why we call this handover as soft handover. So the question is, given why we were not using CDMA and all second generation technologies, given these advantages that are clearly identifiable. So the answer is the CDMA is complex, and at the time when the second generation technologies were proposed, such as the GSM, the processing power required by the CDMA were a little bit high, and this is why the TDMA was adopted in GSM. So the codes that we are using in CDMA in order to achieve the orthogonality of channels, and we will talk a little bit more about this. So in order to allow several users to use the channel simultaneously are the channelization code and the scrambling code. So let's have a look first on the channelization code. Let's consider this simplified scenario in order to understand where do we need the code to differentiate between the traffic. Let's consider two users, and again I repeat, this is a simplified scheme. So I will consider a user A who is sending the following set of data. So I have 1, 1, 0, 0, 0. At the same time, I have another user B sending another set of data 1, 1, 1, 1, and 0. So given that the signals are sent simultaneously, it's normal that the two signals will superpose and add to each other. So I will have the A plus B signal now, which is 2, 2, 0 plus 1, 1, 1, and 0. So suppose the node B will receive this signal. When the node B will encounter a signal, a value of 2, it will deduce that the only scenario is that A is sending 1 and B is sending 1. And when the signal received is 0, the only scenario is that A and B are sending 0. But the problem is that when the node B receives the signal 1, how it can differentiate which user sent 1 and which one sent 0. And this is why superposing these two signals causes a problem, and this is why we need the codes to differentiate between the signals sent by A and B. So the possibility to separate these channels of communication makes the data stream orthogonal. So the orthogonality was provided and applied using the time division. If I want to say how orthogonality was achieved in the TDMA, this was done by providing each user with a frequency channel. How we did this in the frequency division multiple access, this is by providing each user a certain channel. Sorry, in TDMA we provide each user with a time slot in a certain frequency channel, while in the frequency division multiple access, the frequency channel in itself is separated between the different users, and thus each user will have a dedicated frequency channel that he can use. Now in the code division multiple access, the way to provide orthogonality is by using the codes, and we will see how the code will achieve this orthogonality. So the first step to understand is that each user is assigned a certain code, and the code consists of a sequence of chips. And now we define a new concept, which is a chip, which is a binary data, but with the duration is shorter than the duration of 1 bit. So each bit is represented by a certain number of chips. So the chip is in two states. We call this a bipolar states. So it can have two values, 1 and -1, rather than 1 and 0 when we compare this to the bits. Each stream of data, whether for one user or for different users, so each user might have a different types of data, voice, data stream, so control data for a single user. Each type, each flow of data will have a certain sequence of chips, certain code, and thus a certain sequence of chips to represent the bits. Let's have a look now on how to do the encoding, how to transform each bit in a sequence of chips. Let's consider the user A who's sending the sequence 11000, and the code assigned for the user A is 1 minus 1, 1 minus 1. Again, I repeat that each chip can have two states, either 1 or -1. So now each bit will be represented by a sequence of 4 chips. How do we represent each bit? So we can consider this using two aspects. One aspect is that we transform the signal or the data sent by the user A into a bipolar form, which means the 1 will remain 1, but the 0 will become -1. And then we multiply this new sequence, which is now 1, 1, -1, -1, -1, with the code sequence assigned to A. So when I am sending a bit 1 and I multiply 1 by the sequence of the code, the result will be the code itself. And when I have 0, which means in bipolar form it will be -1, the -1 multiplied by the code will reverse or inverse the code. So when I have 1, it becomes -1, and when it is -1, it becomes 1. This is the first way. Or we can directly say that when I have 1, I replace 1 with the code of 4 chips, which is 1 -1, 1 -1. And when I have 0, I reverse the order, so I will have -1, 1, -1, 1. Let's see concretely how to do this. So I will consider A, which is the signal 1100, the data 11000, and B 11110. The code chips for A is 1 -1, 1 -1. The code chip of B is 1 -1, -1, 1. So I will consider the example now. So again, I will repeat. We will have the code for A is 1 -1, 1 -1. The code for B is 1 -1, -1, 1. I will consider a simplified scenario where the data for A is 1 0 0 and the data for B is 1 1 0. So we consider the different possibilities for the combination of bits between A and B. So now the encoded stream of data, we will apply what we have said before for A. So I will replace the bit 1 with the code of A. So the bit 1 will be represented by 1 -1, 1 -1. And as we said before, the bit 0 will consist of inversing the code. So I will have the code inverse, which means 1 -1, 1 -1, 1. Again, the 0 bit will be represented by the inverse of the code. So again, we can say this is the first bit and this is the second bit, and the third bit will be again -1, 1, -1, 1. Let's do the same for B. So if I want to encode the data sent by B, so the first bit is 1, I will use the same code of B, which is 1 -1, -1, 1. and the second bit is again 1, so I will repeat the code again. It will be 1 minus 1 minus 1 1, and now the B is sending 0, so what we will do is to reverse the code or inverse the code, and now it will be minus 1 1 1 minus 1. So as we have done before, A and B are sending the data simultaneously. So the data will sum up, and now let's do the summation for each chip separately. So 1 plus 1 is 2, minus 1 minus 1 minus 2, 1 minus 1 0, and minus 1 1, again it is 0. So minus 1 1, I'm just adding the values, so 0 0 minus 2 and 2, and minus 2 2 0 and 0. So now the node B will receive this signal. How the node B will find the original data sent by A and sent by B? This is done through what we call the correlation. Sorry for the font, but this is the best I can do. The correlation is done by doing multiplying and summing each stream received with the code of the user. So if I want to do the correlation for A, what I have to do is to write the code of A continuously. So I will 1 minus 1, 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 1 minus 1. And then I will do the correlation. So I will multiply, this is similar to the scalar product in vectors. So 2 times 1 plus minus 2 times minus 1 plus 0 times 1 plus 0 times minus 1. So 2 times 1 is 2 plus minus 1 times minus 2 times minus 1 is again 2 plus 0 plus 0. So the result is 4. Again 0 0 minus 2 and minus 2, and then I will add, so 0 plus 0 plus minus 2 plus minus 2, it is minus 4. And now I will do the same for the third bit, minus 2 plus minus 2 plus 0 and the plus 0. So the result will be minus 4. So now when the value is positive, and in general it is equal to the number of chip per bit, in my case I have 1 2 3 4 chip per bit. So when the number is plus 4, it means that the bit is 1. And when the number is negative, and in particular minus the number of chips per bit, in our case minus 4, this means that the bit sent by A is 0. And this is, again, this is 0. And now we could conclude or deduce the values 1 0 0, which corresponds to the data bit sent by A. So we can do the same for B, and by replacing this sequence of chips by the code of B, which is 1 minus 1 minus 1 1, 1 minus 1 minus 1 1, minus 1 minus 1 1, and do the same, and then we will find, we can predict that the results will be 4 4 minus 4, and thus the data of B will be 1 1 and 0. So as we said before, when I replace a bit by a chip, so for instance, if I am replacing one bit with 4 chips, I'm increasing the number of, I will call this the changes of states. So instead of having the signal at one value during the duration of bit, which is, let's say, 1, I will have 4 changes. If I'm representing the 1 with 1 minus 1, 1 minus 1, the signal is changing 3 times during the time period of one bit. So this will spread the frequency spectrum of the transmitted signal over a wider band of frequency, and this is related to the changes of state within a certain time period. The more I'm increasing the changes, I'm repeating the changes during the same time period, I'm occupying a larger bandwidth of frequency. This is why we call this the spread spectrum, or spreading spectrum technologies. And at the same time, when I'm spreading the signal over a wider bandwidth, I'm giving more immunity to certain type of noise, and this is why I'm calling the number of chips per bit the processing gain. So the more I have the number of chips per bit, the more the signal is is immune against certain type of noise. And at the same time, we call this spreading factor, and we'll see this in a few slides. So the channelization code are providing the orthogonality, or the independent channels of communication for different users, or for the same user, different types of data flows. So in the uplink, we are distinguishing user using scrambling code, and we'll see this later on. One important thing is that the codes does not only separate the data sent by different users, but an important thing is to distinguish if a user is sending data or not. So let's consider the following example. So I will reconsider the values I obtained a few slides ago. So I'm having A with code 1 minus 1, 1 minus 1, B with the code 1 minus 1, minus 1, 1, and we'll consider a user C with the code minus 1, minus 1, minus 1, minus 1. So in the data transmission scenario we saw before, the result of the superposition of the two signals of A and B, when A was sending 1 and B was sending 1, was 2 minus 2, 0, 0. So this is the result of the superposition of the data sent by A and B at the same time. So I'm not considering C transmitting any type of data, but how the node B will differentiate that C is not sending a data, neither 1 and nor 0. So this is also done through the correlation. I will correlate the result of A and B superposition with the code of C, and when I do the correlation, I will have minus 2 plus 2 plus 0 and plus 0, which is equal to 0. And when the result of the correlation is 0, this means that no data is transmitted. And I remind you that when the result is plus 4 in our case, or positive value, this means that A is sending 1 or B is sending 1, depending. I'm doing the correlation for A and B. When the result is minus 4, given that I have 4 chips minus the number of chips, and in general when it is negative, this means I'm sending a 0 bit, and when the result is 0, this means that no data is being transmitted for the user in question. So where this magic comes from? What is the magic in these codes that allows us to do the separation of data, the orthogonality of data? The main reason is that the codes we are using are mutually orthogonal. So let's consider an example. Let us see the codes for A and B. So the code for A is 1 minus 1, 1 minus 1. The code for B is 1 minus 1 minus 1, 1. And the code for C is minus 1 minus 1 minus 1 minus 1. So if I do the correlation of A and B, which is between the codes of A and B, it will be, I will write them one over the other. So 1 minus 1. One above the other, 1 minus 1 minus 1, 1. Let us do the correlation of code. It will be plus 1, minus 1, minus 1, and the result is 0. The same will be when I do the orthogonality test for B and C, which is that the correlation of the two codes will be 0. And the same will be for A and C. So when I say the codes are mutually orthogonal, this means that the correlation of any two codes will give us 0 as result. How to generate the code? The family of codes used in the channelization code is the Walsh code. So the Walsh code are generated as follows. I start with the seed, which is 0. Then I repeat the seed right and below. So I will repeat the 0 to the right and to the below. I invert the seed diagonally. So I obtain 0, 0, 0, 1. Then this will be used to generate a longer code. So I will consider the seed, which in my case will be 0, 0, 0, 1. I repeated right, I repeated below, and I inverted diagonally. So the 0 will be 1, the 0 will be 1, the 0 will be 1, and the 1 will be 0. So now I have 4 codes. I can look at this matrix, and the code are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0. And of course, as we said, the code are bipolar, so I will be replacing the 0 with -1, and we will have the following sequence of code which are mutually orthogonal, and you can do the test of orthogonality for these codes. So the number of chips used in wideband CDMA varies between 4 and 256 in the uplink, and up to 512, so 4 to 512 chips per code in the downlink. So as you saw in the previous slide, the number of codes is equal to the number of chips. This is how we generate the codes. So if I have a code of 4 chips, I can have 4 mutually orthogonal codes. If I have a code of 256 chip, I can have 256 mutually orthogonal code, and thus 256 users. And by applying this to the scenario we are talking about, I will have 256 possible, up to 256 users in the uplink, parallel users or parallel codes to be more accurate, and 512 parallel codes for the downlink. And the way we are generating the Walsh code, we are each time multiplying by 2, so the length of the code is always a power of 2. Who will allocate these codes? These codes are allocated by the radio network controller depending on the data rate. I will talk about how we select the length of the code depending on the network condition. So when I have a short code, this means I'm having higher data rate, and I have long code, I will have slower data rate. So what if I have 2 users, one wishing to have a high data rate and the other wants a low data rate, depending on the needs? And as I said, we will explain furthermore where and when we select. So we need these codes to cohabitate. So I need at the same time to have a short code that is mutually orthogonal to a longer code. First, to talk about the orthogonality test, I do the orthogonality test, and given that the codes are always multiple of 2, so this is a longer code, I repeat the shorter code twice if it is half of the longer code, or 4 times or 8 times, and then I do the orthogonality test between the long code and the short code. So I can have at the same time one long code, let's say 512, and 128 chip per code. Another point is that when I'm using at the same time a long code, this will restrict the use of shorter code in order to be capable of distinguishing between the code that is actually used. So we said that we increase the bandwidth whenever we are using more chips per bit, and this will make the signal immune against noise, and at the same time it is spreading the frequency bandwidth, and this is why we use 2 terms to represent the number of chips per bit. We can call this the spreading factor, given that the more the value of the this value is, the more the bandwidth occupied by the signal is. because the signal is making more fluctuation in a given time period. So the spreading factor is the processing gain. And again, I repeat, spreading factor because the bandwidth is increasing when the spreading factor is increasing, and processing gain because the signal is more immune when this value is higher. So, and this is illustrated here in this sentence. So we have a fixed chip rate, which is 3.84 mega chip per second. And and this explains why when we have more chips per bit, the overall bandwidth is less. So if I have, let's say, if the frequency of chips is 3.84 mega chip per second, and if I have a code of 512, you can easily calculate the number of bits per second. And if I have a shorter code, the number of bits per second will be higher. These are numbers that explains the bandwidth allocated, 5 megahertz uplink and downlink. And as in GSM, the data is chunked into frames. So each frame is 10 millisecond long, and so we have the number of frame per second is 100 frame with a simple calculation. And if we apply the 3.84 mega chip per second with 100 frames per second, we can say that per each frame we have 38,400 chips. So this illustrates the UMTS frame, and when we have a spreading factor of 4, of 8, we can see that the number of bits per second decreases when the spreading factor increases. We have 15 slots per frame, and so we have 2,560 chips in each slot, which is a multiple of the length of the code. So if I considering a code of 512 chips, so if I have 2,560 chip per frame divided by 512, so this is an integer number of bits per each slots. So I cannot have a decimal number in that case. So this is an example of the number, how we illustrate this. We'll have, let's say, 5 bits in each slot. So this is what we said before. The spreading factor can be calculated at the chip rate divided by the data rate, and you can do the calculation of any unknown of these three when knowing the two other values. So given that the channelization code can have variable length, so this is why we call them OVSF, for orthogonal variable spreading factor. And we can within the same frame we cannot within the same frame change the length of the code, the spreading code. However, but in two consecutive frames we can have two different spreading code. Why do we have to change? This is to change the length of the code because of the changes that might occur in the network condition. So suppose I'm doing a voice conversation. In such a case, I'm not that interested in having a high data rate, but I need a communication that is very immune against noise. So this is why I will prefer to have a low data rate but a more immune signal against certain types of noise. While in some cases when I'm needing a high data rate, let's say for video streaming, I might tolerate some type of errors that might occur, but I'm more interested in having a high data rate. So this is why I might request a smaller spreading factor in order to have a higher data rate. So one of the main points that needs to be satisfied in order to maintain the orthogonality and thus the good performance and working of the channelization code is synchronization. Because as you can see in the example, when the two codes are not synchronized, which means that the first chip does not of one code does not correspond to the first chip in the second code, in that case, the codes are no longer orthogonal. So let's consider the code. So B have 1 minus 1 minus 1 1, and let's say if I have the C that is 1 1 minus 1 minus 1, that is unsynchronized. This is why we have minus 1 1 1 minus 1. Now the correlation is we can do the correlation. It is -1, -1, -1, -1. So the result is 4, which is different than 0. So the two codes are no longer mutually orthogonal, and thus the orthogonality is lost. And if we apply such code, we will not have the data separated correctly, and we will have erroneous values of the data corresponding to B and C. So the synchronization is a very crucial factor. However, this cannot be applied or provided in certain condition. So one can say, if I'm talking about the data going in the downlink, which means from the node B to the users, so I can say that given that the source of the data is unique, so I can think about a way to synchronize the different user equipments with the node B. So this can be done using the synchronization channel that we will address later on. However, the issue comes when we are talking about the user wishing to send data to the node B, and in such a case, it's not easy to achieve the synchronization necessary to let the channelization code work correctly. So this is why we need the scrambling code that are different from the channelization code, but allows to create the orthogonality of data when the synchronization is not provided or is not achieved. In addition to the importance of the scrambling code in order to provide the synchronization between the different users, the importance of scrambling code is to identify the related node B and to identify the node B for the user, and at the same time the user for the node B. Let's consider these two scenarios. So I have the user A that is located at the boundary of the cell, and at the same time he's receiving two signals, and as we said before, the same frequency can be used in the two adjacent cells, and this is one of the advantages we identified at the beginning of the lecture for the third generation technology. So the user A needs to differentiate between the signal coming from the node B and cell 1 from the node B in cell 2. And this is in the downlink. In the uplink, the node B is receiving on the same frequency the data coming from users within the area of coverage of cell 1, but at the same time the node B is receiving the signal from user C. And the same applies in the node B in cell 2. It receives the data coming from user C and at the same time from A and B. And it's very important for the node B and for the user to differentiate between the two signals, or between the signals coming from different node B in this scenario and the different users in this scenario, such that the node B in this case will consider, the user A will consider the signal coming from node B and will consider that in cell 1 as the main signal, and will filter the signal coming from the node B in the cell 2, will consider it as a noise. In this case, the node B will filter the signal coming from the user C and drop it, while keeping the signals coming from user A and user B, and the same node B in cell 2 will consider the signal coming from user C and it filter and drops the signals coming from user A and user B. So the role of scrambling code, to sum up, is first to solve the problem of synchronization that prevent the correct working of this synchronization code from the channelization code, and second to allow the node B and the user to identify their corresponding users and node B respectively. So the scrambling code, as we say, uniquely identify the sources of signal. Different node B will have different scrambling code allocated to user equipment, and this allows the mutual identification. The scrambling code can be either 256 chip or 38400, and again, this is not related to data rate, and this is why we will not have various or variable length code schemes. We call sometimes the scrambling code as pseudo noise codes or pseudo random codes, given that the way they are generated, or they look like noise. So as you will see, the scrambling code applied to the chip sequence coming encoded using channelization code, there is no spreading factor. A chip will still be represented as a chip. We do this by simple multiplication of the chip sequence coming after the first encoding by the channelization code, and we'll see the overall schema later on. We will multiply this by a scrambling code, and we'll get the scrambling coded chip sequence. Let us look a little bit about how we do this. I will leave the slide to the schema later on, which will clearly explain how we apply the scrambling code and the channelization code, the order of application. And this schema illustrates how, when the data of A and B are correctly extracted, if the codes are synchronized. However, when the codes are not synchronized, the data will not be extracted correctly. This is only an illustration. So the characteristic of gold codes, the family of codes used in scrambling code, is that even though the codes are not synchronized, we are still capable with a certain noise induced to extract the data coming from A and B. So this will solve, it is not that sensitive to the synchronization problem compared to the Walsh code, which are the channelization code. So this is how the order of encoding or application of synchronization code as channelization code and scrambling codes. So let's consider this scenario. This is the node B. This is the downlink channel. So we have data for A that can be user data and control data, and same for B. First, we do time division multiplexing by putting the data in a certain order, putting, let's say, the user data before the control data, depending on the order to be used, and this is not our concern now. So we will do a time division multiplexing. Then we will apply the channelization code. The same will be applied for the B's data. So we superpose the two channelization codes. So far there is no problem, since the code can be easily synchronized. We have the unique source. Then we apply the scrambling code. And again, as I said, the scrambling code is used to solve the problem of synchronization between the node B and the users. So we will send this data through the different channels, and then we will see how we will see in the uplink how A will do. A will do if I have two streams of data. Again, this is a unique source. We have two channelization code, one for each user data. Then we apply the scrambling code and modulate it before sending it in the uplink. So as I said before, the synchronization of user equipment to node B is something that can be done in order to make the channelization code to allow them to work properly. So how to do this? This is done through two channels, one primary synchronization channel and one secondary synchronization channel, used for to make or to align the time slots and the frames between the user equipment and the node B, such that the user equipment will know the start and the end of each frame. So again, we use this in order to allow the synchronization of channelization code first, and then allow them also to work the scrambling code of the node B they receive the signal from. As a summary, we need to identify two boundaries, or the start and the end of two things. First, we need to identify the start and the end of each time slot, each slot in each frame, and we said before that each frame consists of 15 slots. And once we identify the boundaries of a slot, we need to identify the boundary of the frame, and after that we can start reading correctly the data and achieve the synchronization between the user equipment and node B. So we have, as we said, we have two synchronization channel, the primary synchronization channel and the secondary synchronization channel. When the user equipment is on, it starts listening to the primary synchronization channel. And the node B is transmitting throughout this channel a certain code repetitively. And each code takes one time slot. So we can illustrate this like this. We can see that we have one frame that consists of 15 slots, and we are sending the code repetitively on each slot. So when the user listens to this channel, so it will look for this known code. And when the user identifies the beginning of this code, now he knows that this is the beginning of a slot. So again, knowing the beginning of the slot does not mean that we know now where the frame begins. So now suppose I identify this as the beginning of the slot. I'm not sure if this is the first slot of the frame, the second, the third, the fourth, or the 15th. So this is why we need to switch to the secondary synchronization channel in order to align the boundaries of the frame. So the secondary synchronization channel transmits a sequence that occupies a whole frame. The sequence is repeated in all frames. The difference between the primary and secondary is that the primary channel, the code is repeated every slot. Now, when we know the beginning of each slot, we have to look for the beginning or the start of each frame, the boundaries of the frame. So we have to listen on the secondary channel and compare the data we are reading with a list of 64 blocks. So when we identify a certain sequence that corresponds to one of the 64 possible sequences, we know where the sequence begins is the beginning of the frame. Now, knowing the beginning where the frame begins, now I can start reading the data from the data channels. As we have seen before in the second generation, we are always looking to enhance the data rate. So we saw the third generation, and then we have the enhancement of the third generation, which does not constitute a new generation, but rather an in-between generation. So we have seen this in the 2.5 generation as an intermediate, or 2.75 generation, the GPRS and the Edge technologies as a bridge between the second and third generation. And now we have the high-speed packet access, whether downlink or uplink, as an in-between generations or in-between technologies between the third generation and the fourth generation. So, but how to achieve higher data rate? We can have more frequencies available for individual cells and allocate more than one channelization code for the users. However, we can still have a certain limitation that we cannot bypass. So this is why the trend was to look for new multiple access technology. And as we said before, we need more frequency bandwidth in order to allow the user to get higher bitrate. But the CDMA cannot work efficiently for wide bandwidth. And this is why we had to look for a new or other multiple access technologies that works well for wider bandwidth. And this is why the scientists working in this field looks for other technologies used in wide bandwidth, and they saw the OFDMA, which is the orthogonal frequency division multiple access that is used in the Wi-Fi technology 802.11g standard, and with channel width of 20 megahertz. So what is OFDMA? As we said, this is orthogonal frequency division multiple access. It is based on the OFDM technology, the orthogonal FDM. Instead of using This is the frequency division multiplexing, which means that the frequency bandwidth is divided into a certain number of channels, with difference of classical frequency division multiplexing, where the carriers should be separated by guard bands. The OFDM allow the use of many wireless carrier signals known as subcarriers at different frequency, but that can overlap. So this is a classical frequency division multiplexing. You can see the guard band between each two carrier frequencies, but in our case in the OFDM, the subcarriers can overlap, and we can look at them like this. This is a carrier, and this is the second subcarrier, and this is the third subcarrier. We have a specific property of the subcarriers that allows them to work well even when they overlap, which cannot work in a classical frequency division multiplexing. Now let's move and talk about the modulation and symbols. You know the definition that any modulation is based on the changes of the characteristic of the carrier frequency, whether the amplitude, the frequency, or the phase, in order to let this carrier hold certain type of data. Usually we use the term modulated or modulation whenever we are transmitting analog data. But in our case, even though the term modulation is still valid, but we will use the term shift keying in order to differentiate the use of the modulation of digital data. So instead of saying amplitude modulation, we would say amplitude shift keying, frequency shift keying, and phase shift keying. It's important to mention that the amplitude shift keying can be problematic because the circuitry used to generate and transmit varying amplitude tends to be inefficient. And another concept that we have seen before also is the multi-level signaling, where we, instead of sending one bit at a time, we can send one symbol that consists of more than one bit. We have seen this in the memory technologies, and we have seen this also in the telecommunication technology. In this scenario, we have each symbol consists of 2 bits. So the symbol period is the same as when I have multi-level signaling. During the 1-bit period, I'm sending a symbol, but the symbol consists of more than 1 bit, and this is why with the multi-level I can achieve higher bit rate. So we are decreasing the bit duration compared to the previous example. How do we achieve orthogonality? The first characteristic that we will be using in OFDMA, in quadrature amplitude modulation, is the orthogonality between sine and cosine. We have seen the orthogonality in discrete signals, when we have seen the 1 minus 1, 1 minus 1, that is orthogonal to 1 minus 1 minus 1, 1, and we did the correlation and we find that the result is 0. Now we are working in a continuous signal, and we will see that the sine wave and the cosine wave are orthogonal. Let's look at these two signals. The first is the sine theta, and the second is the cosine theta. If I multiply them, I will have the sine theta cosine theta. In the correlation used in discrete signals, we did the summation. So we multiplied, for instance, 1 times 1 plus minus 1 times minus 1 plus 1 times minus 1 plus minus 1 times 1. So the addition or the summation in the discrete signal corresponds to the integral in the continuous signal. And the integral, for those who are familiar with, is the summation of the area between this signal and the x-axis. So this is a plus, and this is minus, and this is plus, and this is minus. If I do the summation, I will see the same area above the axis is equal to the area below the axis. So when I do the summation, the result will be 0. And this is why these two waves are orthogonal. In contrast with two other, let's consider sine theta and minus sine theta. If I multiply them, I will have the minus sine square, which is all below the axis. So it is we have minus and minus, so which cannot be 0, and thus these two waves are not orthogonal to each other. The fact that these two waves are orthogonal, so if I change the amplitude or phase on the sine wave, does not affect the amplitude and phase on a cosine wave, and vice versa, and thus I can do the modulation on one of these waves and use them to transmit data without affecting the second one, and vice versa. So this means that we can use them separately to represent data, and then we can extract the data by correlation that is adapted in continuous signal. And this is the main concept we use in quadrature modulation, where we transmit a superposition of a modulated sine wave and modulated cosine wave. And then at the receiver side, as we did in the discrete signals, we have to multiply the superposition of carriers by a synchronized sine wave to get the first user's data, and synchronized cosine wave to get the second user's data. So we represent this using what we call the constellation diagram. We have the I-axis that corresponds to the in-phase component and the quadrature phase component, the sine and the cosine wave. So these are the modulated values, and then we call this the quadrature phase shift keying. So these are the two carriers used. For practical reason, we will not use I and Q, and then we'll use some superposition of I and Q, and this is why we will have this constellation diagram, 1, 1 or 1, 0, 1 corresponding minus I plus Q, minus I minus Q, plus I minus Q. So this is for practical reason we use such type. In addition, in order to increase the bit rate and the number of symbols, in order to have more than bits per symbol, more than 1 bit per symbol, 2 or 4, so we use the amplitude modulation in addition to the phase shift keying, the amplitude keying in addition to the phase shift keying. So we use more than one value of superposition of I and Q. So this will increase the number of symbols. In the previous scheme we had 4 symbols, thus we can have 2 bits to be represented per symbol, and now by changing the amplitude we can get up to 16 symbols and thus 4 bit. And finally, we can quickly say that compare how many additional bits represented by each blob in 16 cam. QPSK quadrature phase shift keying, we have 4 phase shift keying, and thus we have 2 bits, while in 16 cam we have 4 bits. Binary phase shift keying, we have 2 states, which means 1 bit, and thus we can see the difference compared between the 16 cam and the QPSK and BPSK. We said before that why do I need these different encoding schemes? When I have more symbols and thus high data rate, and when the symbols are close together, the problem is that when I have a noise, there is a higher probability to have some error when the value of one symbol will be confused with the value of another symbol, because the symbols become tight. So this is why we cannot select higher bit rate when we have, let's say, the 64 cam, which provides the higher bit rate, if the channel condition is not good. So I can, when the conditions are not favorable, I can move from higher bitrate encoding schemes such as the 64 cam to QPSK, which is the 4 cam. And when I have the good conditions for the channel, I can move back to get a higher bitrate, and then I can move to 16 cam or 64 cam.